everyone, and welcome to our presentation. We are GeoBlast Pioneers, a group of final year engineering students from the Department of Earth Resources Engineering, University of Moratuwa. Today, we're proud to present our design project titled Optimized Rock Blasting Model for the Lower Malwathu Oya Reservoir Project. Our project focuses on developing a safe, efficient, and cost-effective blasting model that can support both rock excavation and sustainable dam construction. Before starting the design, we first identified and analyzed the actual Lower Malwathu Oya blasting site using Google Earth Pro. Here, you can see the Thanthiramala region in the Anuradhapura district, where the spillway excavation is located. We zoomed into the exact blasting coordinates provided by the project team to clearly visualize the topography and surrounding features. The site lies along the 369 Grama Niladari division within the Mahawilachchia area. Using elevation profiles, we could observe the bench levels, rock exposure, and slope angles, which were later used to plan the bench height and hole orientation. This virtual observation helped us understand the geological setting, nearby water bodies, and potential safety zones. The Lower Malwathu Oya project is one of Sri Lanka's major irrigation and water resource developments. During spillway construction, a large biotite gneiss rock mass obstructed the alignment. To remove this, we applied controlled blasting techniques while reusing the fragmented rock as riprap for the dam's upstream embankment. Our main goal was to achieve the required 300 to 400 mm fragment size range safely and efficiently, while minimizing environmental impacts. The key objectives of our project were to design an optimized blasting model for biotite gneiss formations at the Lower Malwathu Oya blasting site, to achieve the desired rock fragmentation suitable for dam embankment construction, to ensure minimum ground vibration, reduced fly rock, and environmental compliance. And finally, to improve cost efficiency while maintaining safety and productivity on site. We began by identifying the major parameters that influence blasting performance. The burden and spacing ranged between 1.1 and 1.4 meters, with a hole depth of around 3 meters and a diameter of 38 millimeters. We used ANFO as the main explosive with a water gel primer, fired through non-L delay detonators with delays from 0 to 200 milliseconds. Both square and staggered blasting patterns were analyzed for comparison. Our target was a 300 to 400 millimeter fragment size to be used as riprap. Fragmentation quality depends on parameters like rock strength, burden, spacing, and charge per hole. We used JK SimBlast and 2D Bench software to simulate different blast conditions, optimizing the powder factor, timing, and stemming to reach the ideal fragment size distribution. Next, we used the JK SimBlast software, together with 2D Bench, to simulate and analyze our blasting designs. In this demonstration, we began by setting up the bench geometry, defining the height, free face, and burden line according to the site parameters. Then we entered the blast pattern, including hole spacing, diameter, and depth based on our design sheet. The software allowed us to input explosive details, such as ANFO and water gel quantities, delay sequence from 0 to 200 milliseconds, and staggered or square arrangements. After configuring all 6 design variations, we ran the blast simulation to generate the predicted results. The output showed fragmentation curves displaying the proportion of material below 300 and 400 millimeters. It also plotted air blast pressure and peak particle velocity graphs, helping us assess both performance and environmental impact. Through repeated simulation and adjustment, we identified Design 4 as the optimum model, achieving the best fragmentation, lowest vibration, and acceptable powder factor. This process clearly demonstrated how digital simulation tools can minimize trial and error and improve the precision of real-world blasting operations. environmental and safety concerns such as ground vibration, fly rock, air blast, and dust generation. To mitigate these, we controlled the charge per delay, applied quarry dust stemming to confine gases, and carefully selected delay intervals to reduce simultaneous energy release. We also followed proper explosive handling procedures, ensuring all operations met national safety standards. Our methodology followed several key steps. First, we characterized the rock mass and site conditions at the spillway area. Then we defined design objectives and constraints, followed by collecting baseline parameters from similar Sri Lankan quarries. Next, we developed preliminary designs using AutoCAD and simulated them using JK-SimBlast. Finally, we analyzed fragmentation curves, vibration data, and costs to identify the best model. Using JK-SimBlast, we created multiple simulation scenarios by varying burden, spacing, and explosive charge. The software generated fragmentation curves based on the Kuzram model, predicting particle size distribution. It also calculated peak particle velocity and air blast levels to evaluate environmental effects. These simulations helped us fine-tune each design before recommending one for field use. In total, we developed 6 main designs. Designs 01 to 05 were based on ANFO with different charge amounts, burdens, and spacings. Design 06 used a split blast technique with water gel explosives only, aimed at better control and safety. Our objective was to compare these patterns for the best fragmentation, lowest vibration, and most economical outcome. After analysing all models, Design 4 was selected as the optimal configuration. It used 1.30 kilograms of ANFO and 0.125 kilograms of water gel per hole, with a burden of 1.2 meters and spacing of 1.35 meters. The pattern was square, and it achieved a powder factor of 0.30 kilograms per cubic meter, PPV of 0.11 millimeters per second, and an air blast of 135 decibels, all within safe and efficient limits. We also compared the economic performance of each design. The costs included explosives, drilling, charging, and detonators. For Design 4, the total cost per blast was about 69,000 rupees, making it the most cost-effective option. In contrast, the split blast design cost more than 300,000 rupees per blast, so it was rejected due to high material and handling costs. During analysis, we found that optimizing the powder factor significantly improved both fragmentation quality and cost efficiency. The Kuzram fragmentation curves confirmed that Design 4 achieved the desired 300 to 400 millimeter fragment range while maintaining safety. Although the split blast method gave finer fragments and very low vibration, its high cost and operational complexity made it unsuitable for large-scale use. Therefore, our chosen design balances technical performance, environmental safety, and economic feasibility. In conclusion, our optimized blasting model, Design 4, proved to be the most effective for the Lower Malwathu Oya project. It ensures efficient fragmentation, low vibration, and cost savings, meeting all project requirements. For implementation, we recommend blasting 17 days per month, with 5 blasts per day to complete excavation within 6 months. Future work will involve field validation, continuous monitoring, and further refinement for other similar rock formations across Sri Lanka. We are Geoblast pioneers. Amrathunaga LMIA, Madhusankar WA, Mayadune KMGS, Nadisha MKP, and Sivajan R. We would like to express our sincere gratitude to Dr. S.P. Chaminda, our internal project supervisor, and our sincere gratitude to Engineer S. Sabasan, our external project supervisor, for their valuable guidance and support throughout this study. Thank you very much for your attention. We hope this presentation gave you a clear understanding of how our optimized blasting model contributes to efficient and sustainable rock excavation at the Lower Malwathu Oya project. Once again, we are the GeoBlast pioneers, committed to engineering innovation for a sustainable future.